A single loose wire inside a high voltage switchboard was enough to shut down a massive container ship loaded with thousands of tons of cargo. Is this believable, or does it sound too convenient? This is an example of the terminal as stated in the NTSB report. The only difference is that there are no labels here to cover the ferrule, so we just simulated by inserting the cable about halfway through. Then we tested the grip by pulling on the wire. As we can see, even though it was inserted only halfway through, we couldn't pull it out. There are moments in maritime history that force the industry to stop and pay attention. Moments that remind us that even with modern automation, electronics, and safety systems, a single point of failure can still trigger a catastrophic chain reaction. The DALI blackout and everything that followed is one of those moments. But this isn't just a story about a power loss. It's about design philosophy, operational discipline, system redundancy, and how modern ships have advanced faster than the safeguards meant to protect them. So today, we're going to break it down: the engineering, the investigation, and the lessons every maritime professional needs to understand. According to the NTSB, the entire sequence began with something remarkably small: a single loose signal wire. Because its label sleeve covered the ferrule, the wire never fully locked into the spring clamp terminal. At first, it worked, but with higher resistance and weak mechanical grip. Over time, vibration and thermal cycling loosened it further until it finally disconnected. When it did, that single wire triggered a breaker trip and shut down the ship's low voltage system, the network powering steering, cooling pumps, automation, lighting, and all auxiliary systems needed to keep propulsion online. Without it, the ship wasn't just dark, it was uncontrollable. From a technical standpoint, the chain makes sense: a small installation oversight that left the wire loose and vulnerable. A tiny detail with ship-wide consequences. So, vibration and heat got the wire loose? Let's try that out. This is an example of the terminal as stated in the NTSB report. The only difference is that there are no labels here to cover the ferrule, so we just simulated by inserting the cable about halfway through. Then we tested the grip by pulling on the wire. As we can see, even though it was inserted only halfway through, we couldn't pull it out. So we tried to release it a bit more to see what happens. Still nothing. So we tried to release it some more, all the way to where there will still be some minimum amount of grip on the cable, just to simulate what was described on the report. As we can see, even with minimal contact remaining, it still took some effort before the wire was eventually pulled. The question is this believable, or does it sound too convenient? The NTSB didn't arrive at this conclusion by guessing. They had physical evidence of how the wire was installed, they understood the known failure behavior of spring clamp terminals, and they confirmed the missing signal directly triggered the breaker trip that began the blackout sequence. So, from an engineering and forensic perspective, this failure is entirely plausible. The real question is, how likely is it? Can a single mislabeled wire normally shut down a modern ship? For one vessel on one day, the odds are extremely low, but still never zero. Across thousands of ships and millions of terminals, a workmanship error like this will eventually align with the wrong function at the wrong moment. That's the Swiss cheese model: small defects lining up to create a pathway to failure. And that's exactly what happened aboard the DALI. A rare, low probability event amplified into a high impact blackout because the system wasn't resilient enough to survive it. One part of the report that immediately stood out to me was a section describing safety concerns that weren't the cause of the first blackout, but directly affected the ship's ability to recover propulsion and steering afterward. The first of those was the main engine shutdown logic tied to the low cooling water pressure. The report states this configuration was installed at the shipyard and met class requirements at the time. But the NTSB concluded it ultimately increased risk because the engine shut down when its cooling pump lost power after the blackout. From personal experience, 25 years at sea, 13 of those as chief engineer on tankers, VLCCs, bulk carriers, and container ships, I have never seen a main engine programmed to shut down simply because cooling water pressure dropped. It's not unheard of, but very uncommon, and in my view, not good engineering practice. In today's safety mindset, that actually borders on a design flaw. With a modern electronically controlled MAN B&W ME engine, the automation philosophy should reflect a simple rule. Propulsion continuity comes first over machinery protection, unless there is an imminent threat of catastrophic damage. In confined waters, losing propulsion is far more dangerous than temporary high jacket cooling water temperatures. That's easily remedied and doesn't have an immediate effect on any of the engine components. Shutdowns are typically reserved for truly critical events, such as low lube oil pressure, crankcase overpressure, which can cause explosion, engine overspeed, critical automation or control failure, emergency stop or fire integration, or hydraulic system failure in the case of electronically controlled engines. Anything less severe normally triggers a slowdown or just an alarm, and not stop the engine. So yes, class permitted shutdown at low cooling pressure, but it is not required. The shipyard's choice was compliant, but operationally questionable because it prioritized equipment protection over vessel maneuverability. In this case, compliance existed, but logic did not. Anyway, since there was a blackout, the lube oil pump and the hydraulic pump definitely lost power. Any one of those is enough to trigger a shutdown. I think the NTSB just wanted to point this out as an additional risk in case of future occurrences. The next finding focused on the flushing pump, a piece of equipment that was never intended to support critical ship operations. From my own experience, especially working with Hyundai Himson engines, the same type installed on DALI, flushing pumps have a very specific purpose: flushing fuel lines during maintenance or when switching fuel grades. They are small, temporary use pumps. They are not designed to supply fuel to generators during normal operation. That job belongs to the dedicated fuel supply and booster pumps, systems designed with redundancy, automation, and sufficient capacity in mind. But on the day of the casualty, that wasn't how the system was running. The flushing pump had become the primary source of pressurized fuel for diesel generators 3 and 4, the generators that were powering the ship at the time. So instead of a properly engineered, fault-tolerant fuel system supporting the power plant, the ship's operation was relying on a maintenance pump never meant for critical service. And that decision mattered. The flushing pump had no redundancy, there was no standby pump, no automatic switchover, no protective logic, and importantly, no automatic restart after a power loss. So when the first blackout occurred and low voltage power was lost, the flushing pump stopped, and it stayed off. With insufficient fuel pressure, generators 3 and 4 shut down, leading to the second blackout, affecting both the high and low voltage systems. Remember on my previous video when I mentioned this? This time the trip occurred from the generator breakers and not the transformer breakers. This means there was something wrong with both of the engines, as they happened at the same time. These breakers will usually trip in case of engine overspeed or slowdown. The report didn't mention the cause, but I'm leaning towards slowdown due to fuel issues. Whatever it is, it's something common to the two running generator engines, and fuel is the most likely suspect. Turns out it really had something to do with the fuel. Although I was under the assumption that the normal setup of the fuel service system meaning the fuel supply and booster pumps, was being used. That's why I found the visible smoke very strange, because the generators were supposed to be powerful enough to handle the electrical load demand when power is restored. Apparently, since the flushing pump was being used after the initial blackout, it didn't restart. But the generators 3 and 4 kept running because fuel was still being fed to it by gravity. And that small amount of fuel pressure was enough to keep the generators running because there was no electric load at the time, since the 440 volt bus was disconnected. However, when the 440 volt bus was reconnected, there was a sudden surge of power demand due to some of the essential machinery automatically starting up. This meant that the generators needed more fuel immediately in order to compensate. But since there was no pump supplying fuel, only gravity, the generators were in a way overloaded, starved of fuel, and started losing speed, eventually hitting the low frequency, which will cause the engines to trip, thereby causing the second blackout, which, as shown in my previous video, originated from the generator breakers. What makes this even more concerning is that the ship had already experienced 2 blackouts the previous day due to the exact same issue while still in port. Yet the vessel sailed without addressing it. The investigation concluded that while this pump configuration did not cause the first blackout, it severely impaired recovery. The system relied on perfect timing and manual intervention to restore fuel pressure, and in blackout conditions, that's not just impractical, it's unsafe. And perhaps the biggest lesson is this: this wasn't an isolated mistake. Apparently, the same setup was found on at least one other vessel in the same fleet. A workaround, likely intended to be temporary, eventually became standard practice. Sad to say, this was an operational oversight, and as much as NTSB doesn't want it to appear as human error in their report, it clearly is. It's a classic issue of we've always done it this way. The next safety issue involved the configuration of the ship's high voltage breakers, specifically the ones controlling the step-down transformers that power the low voltage electrical system. These breakers were designed to operate in 2 modes, automatic or manual. In auto mode, if a blackout occurred, the system would detect the power loss, transfer the load to the alternate transformer, and restore low voltage power in roughly 10 seconds, fast enough to keep core systems alive and prevent a full operational collapse. But on board DALI, the breakers weren't in automatic. They were set to manual. So when the blackout hit, the breakers opened as expected and then simply waited. No restart, no transfer, no recovery attempt. The only way to restore power was for a crew member to physically go to the switchboard and close the breakers by hand. There was no procedure requiring the breakers to operate in automatic mode, and no regulation enforcing it. So while the configuration technically complied with requirements, it lacked standardization and operational reasoning. It appears the setting was based more on habit than on risk awareness or system resilience, and that choice had an impact. Manual mode didn't cause the blackout, and switching to automatic wouldn't have stopped it, but it dramatically changed the recovery. Instead of a 10-second interruption, the blackout lasted nearly 58 seconds. And when propulsion, steering, and control systems are offline, especially in restricted waters, 58 seconds isn't just a delay, it's practically an eternity. Again, it's the culture of we've always done it this way. It is vulnerability, and in the end, the hardware worked exactly as configured. But the problem wasn't the equipment, it was the decision behind how it was set. The next safety concern focused on the ship's emergency diesel generator, the one system designed to bring essential power back when everything else goes dark. Under SOLAS requirements, An emergency generator must be able to start and supply power within 45 seconds after a loss of low voltage power. That requirement exists for a reason. In a blackout, systems like navigation, equipment, steering controls, internal communications, and emergency lighting need to return quickly because maintaining control depends on it. On DALI, the emergency generator did start, but not fast enough. Instead of restoring power within 45 seconds, it took 70 seconds. As some of you might remember, I also pointed this out on my previous video. Now, according to the crew, the emergency generator automatically started and connected to the emergency bus shortly after the blackout. But as we have seen in the footage, the navigation lights remained off together with all the other lights for about 59 seconds. If the emergency generator did indeed run and connect shortly after the blackout, we would have seen only the nav lights turn on first, followed by everything else once power was restored. Apparently, the delay wasn't caused by a mechanical failure or an unsuccessful start attempt. It came down to something more basic, a limit switch on the ventilation damper. Before the generator could run, a ventilation damper needed to open, and a limit switch had to confirm that the damper was fully open. During the blackout, that confirmation didn't arrive in time due to unknown circumstances. Whether the damper moved slowly, the actuator lagged, or the signal was delayed isn't clear. But until the system received that confirmation, the start sequence won't move forward. So the generator wasn't waiting on fuel, lubrication, or synchronization. It was waiting on one sensor. A few seconds of delay ultimately resulted in a 25-second exceedance of regulatory limits. And when a vessel is adrift without propulsion or steering, those seconds matter. This was a reminder that automation, especially in critical safety systems, is only as strong as its smallest interlock. On board ships, it's always standard practice that the emergency generator must be kept free of any obstacles for it to start automatically as fast as possible. In most of the ships I served on, these generators started automatically within 15 seconds, and we test them on a weekly basis. In my opinion, that radiator damper should have been kept open by default. On board the ships I served on, there were no sensors on the dampers that would prevent the emergency generator from running. In any case, the configuration most likely met regulatory requirements. But once again, meeting the rules wasn't the same as being prepared for reality. At first glance, the DALI incident may look like a rare anomaly, a one-in-a-million chain of failures that happened at the worst possible moment. But when we peel back the layers, what remains is a reminder. Modern ships aren't just steel and machinery. They're systems of automation, control logic, assumptions, and human behavior. And failures in systems like these rarely start with something dramatic. They start with something small. A mislabeled wire, a configuration no one questioned, a setting left in manual, a temporary workaround that quietly became permanent. None of those things alone crippled the vessel, but together, in sequence, they created a situation no crew could recover from in time. And that's the real lesson. Safety at sea isn't about eliminating every failure. It's about ensuring the ship can survive failure and recover. It's about redundancy with purpose, configuration with intention, and operational practices that evolve with technology, not lag behind it. So we have two choices. We can say, this was unlikely. It won't happen to us. Or we can ask, what parts of our operation are we trusting without question? And how prepared are we if they don't respond the way we expect? And that is how safety improves, not through blame, but through awareness and adaptation. So to every engineer, officer, superintendent, auditor, and shipyard technician watching, don't just trust the process. Look closer analyze, challenge. Because at sea, the line between control and chaos can be thinner than a single loose wire. Thank you for watching, and see you on the next one.